Assalamu alaikum, dear students. In today's lecture, we'll continue 6th chapter, which is about counting. And in this lecture, we are going to cover 6.3, 6.4, 6.5 articles of the book. So, a summary of the lecture is as follows. First, 6.3 consists of permutations and combinations. 6.4 is about binomial coefficients and identities. 6.5 is about generalized permutations and combinations. So first of all, 6.3, which is about permutations and combinations, and you are already familiar with the concept of permutations and combinations. We are going to review it with examples and few definitions. So summary of this section uh, consists of permutations, definitions of permutations and few examples, definition of combinations and few examples, and then combinatorial proofs. So first of all, permutation, definition of a permutation. A permutation of a set of distinct objects is an ordered arrangement of these objects. An ordered arrangement of R elements of a set is called an R permutation, right? So the point here to be noted is that order matters in such arrangements. So let's suppose we have a set 1 to 3. The ordered arrangement 3 1 2 is a permutation of S. That is 3 1 2. This order matters. 1 2 3 is different from 3 1 2. So the ordered arrangement 3 2 is a 2 permutation of S. It consists of two elements. We are arranging two elements out of these three elements. So this is called 2 permutation. If we are arranging R elements out of n elements, then this is called R permutation. So the number of R permutations of a set with n elements is denoted by PNR. And the 2 permutation of set 1 2 3 are 1 2, 1 3, 2 1, 2 3, 3 1, 3 2, and hence the total number P32 is equal to 6. So 1 2 3 4 5 6, you can count them. Uh, so we have a formula for the permutations, arm permutations. Theorem 1 gives us a formula if n is positive integer, so keep it in mind, n is positive integer and r is an integer which lies between 1 and n. Then there are p and r, which is equal to n into n minus 1, n minus 2 up to n minus r plus 1 r permutations of a set with n distinct elements. Okay, so similarly, p and 0, if r is equal to 0, is 1, since there is only one way to order 0 elements. So this is the particular case of permutations. Arrangement of 0 elements out of n elements is 1. So corollary. Now this actually leads us to another formula which is stated in the corollary of this theorem. This gives us n factorial, that is p n r is equal to n factorial divided by n minus r factorial. It can be derived from this formula. Okay, so let's have a look at few examples of permutations. How many ways are there to select a first prize winner, a second prize winner, and a third prize winner from 100 different people who have entered a contest? Okay, initially we have 100 different people. That is, for a first prize winner, there are 100 choices. Okay, when first prize has been given to someone, then there are 99 choices for second prize winner, and so on. For third prize winner, there are 98 choices. So the total number of ways to select first prize winner, second prize winner, and third prize winner is P103, which is equal to 100 multiplied by 19 multiplied by 19, and this is 970200. Okay, next example. Suppose that a saleswoman has to visit 8 different cities. She must begin her trip in the specified city, but she can visit the other 7 cities in any order she wishes. How many possible orders can the saleswoman use when visiting these cities? Okay, the first city has already been chosen, so this is fixed, and the rest are ordered arbitrarily. So hence the orders are 7 factorial, 7, 6, 5, 4, 3, 2, 1. Because she has to go to every city. So when seventh city has been chosen, then there are 6. Then uh, she is going to choose second city, and she has 6 choices. And then third city, for third city she has 5 choices, and then 4, and then 3, and then the last city she has only one choice. So if she wants to find the tour with the shortest path that visits all the cities, she must consider the 5040 paths. So there is another other example. How many permutations of the letters A, B, C, D, E, F, G, H contain the string ABC? Now, in this case, ABC is fixed. Okay, ABC can be considered as one object, and D, E, F, G, and H are different objects. So we have 1, 2, 3, 4, 5, 6. 6 objects to be arranged. For the first place we have 6 choices, then for second place we have 5 choices, and so on. 6 factorial choices are there, which makes 720 ways. Another example: in how many ways can we select 3 students from a group of 5 students to stand in the line for a picture? Okay, in how many ways can we arrange all 5 of these students in a line for a picture? So first, this question has 2 parts. The first part actually is, in how many ways can we select 3 students from a group of 5 students, okay, to stand in the line for a picture. So if we have to fill 3 places, and initially we have 5 students, so for first place we have 5 choices, for second place we have 4 choices, and for third place we have 3 choices. So in total, multiplication rule will be used. So we have 60 choices, and this makes us this is actually in terms of permutation P53. Now, if we want to arrange all 5 for the picture, so for first position there are 5 choices, and second position there are 4 choices, and third position has 3 choices, and so on. 120 ways to arrange all 5 students in a line for a picture. Next, uh, counting concept is combination. So as we saw that in permutations, order of arrangement matters, but in case of combination, order doesn't matter. You can understand this as when you choose a few subjects, uh, then this is called combination of subjects, because order doesn't matter. If I choose maths, mathematics, statistics, economics, and if I say in this order: mathematics, statistics, economics, and then I say economics, mathematics, and statistics, and then I say statistics, mathematics, economics, uh, apparently they seem to be different, but uh, this is one combination. So this is how you can understand the idea of combination. In this case, order doesn't matter. So an R combination of elements of a set is an unordered selection. So this is the point to be noted, is an unordered. Order doesn't matter in this selection. Unordered selection of R elements from the set. Thus, an R combination is simply a subset of a set with R elements. The number of R combinations of a set with n distinct elements is denoted by CNR, or sometimes we use this notation, NCR or CNR. This is also called combination of n objects selecting R at a time, is also used and is called binomial coefficient. So this is called binomial coefficient, and we'll learn in section 6.4. Now example for combinations, let S be the set ABCD, then ACD is a 3 combination from S. It is the same as DCA, because order doesn't matter, so ACD and DCA is the same arrangement, since the order listed does not matter. So C42 is equal to 6, because the 2 combinations A, B, C, D are the 6 subsets A, B, A, C, A, D, B, C, B, B, and C. Since order doesn't matter, so A, B, and B, A is one arrangement. So C42 is 6. Now this theorem gives us the formula for combinations of n objects selecting r objects, which is equal to n factorial divided by n minus r factorial to r factorial. And the condition on r is greater or equal to 0 and less or equal to n. Now examples: how many poker hands of 5 cards can be dealt from a standard deck of 52 cards? Also, how many ways are there to select 47 cards from a deck of 52 cards? Now it has again two parts. So first part, how many poker hands of 5 cards can be dealt from a standard deck of 52 cards? So order of cards doesn't matter. So if we have to choose 5 cards out of 52 cards, then the number of ways are C 52 5. And using formula n here is 52, r here is 5. So using the formula we just learned, we have 2598960 ways. So next part of the question, how many ways are there to select 47 cards from a deck of 52 cards? Again, since order doesn't matter, so the number of ways to select 47 cards out of 52 cards is C5247, and using the formula we have answer 2598960. And you can see that 47 is actually 52 minus 5, right? 52 minus 5, and in both the cases answer is same, right? So if this is r, this is n minus r, and n here is 52, and both the answers are same. You can observe that. So next corollary leads us to the result which is discussed in this example, that is combination nr is equal to, that is r combination is equal to n minus r combination, right? If we arrange r objects out of n objects, and if we arrange n minus r objects out of n objects, result will be the same. And we can prove this by formula. So it's really easy to prove. And next, there is another type of proof which is called combinatorial proof. And in this proof, a combinatorial proof of an identity is a proof that uses one of the following methods. A double counting proof uses counting argument to prove that both sides of an identity count the same objects but in different ways. And the other way, a bijective proof shows that there is a bijection between the sets of objects counted by the two sides of the identity. So we can use formula straightforward, or we can use any of these ways, combinatorial proofs as well. So this is the example of combinatorial proof. We have already seen the proof of this result with the help of formula. But bijective, if we consider the bijective proof in this case, suppose that S is a set with n elements, okay, and the function that maps a subset A of S to A complement. If A has R elements, then A complement has n minus R complement. So if S has n elements, is a bijection between the subsets of S with R elements and the subsets with n minus R elements. Since there is a bijection between the two sets, and they must have the same number of elements. So bijective mapping is 1-to-1 and 1-to, and this proves that the number of elements in a set in two sets are same. Double counting proof, by definition of the number of subsets of S with R elements, is CNR. Okay, each subset A of S can also be described by specifying which element are not in A. That is, these elements are in A complement. Since the complement of a subset of S with R elements has n minus R elements, therefore these elements are C and n minus R, and both of both the numbers are equal. Now examples: how many ways are there to select 5 players from a 10-member tennis team to make a trip to a match at another school. Now, selecting members of team is usually a counting problem which can be solved by combinations. So we have to choose 5 players out of 10 players. So number of ways are combinations of 5 combinations. Okay? And where n is 10. A group of 30 people have been trained as astronauts to go on the first mission to Mars. How many ways are there to select a crew of 6 people to go on this mission? Again, combination problem order doesn't matter. So 30 C36, and with the help of formula we can find the answer. Next, how many bit strings of length n contain exactly r ones? So length of bit string is n, okay, and how many bit strings contain exactly r? So again, NCR bit strings uh, which contain exactly r ones. Next example, suppose that there are 9 faculty members in the mathematics department, 11 in the computer science department. How many ways are there to select a committee to develop a discrete mathematics course at a school if the committee is to consist of 3 faculty members from the mathematics department and 4 faculty members from the computer science departments? Now, mathematics department has 11 members and we have to choose how many from mathematics department, select a committee to develop discrete mathematics. 3. We have to choose 3 out of 11 and oh sorry, 9 faculty members in mathematics. So we have to choose 3 out of 9 and computer science department has 11 and we have to choose 4 from computer science department. So from mathematics department, how many ways are there to choose 4 members? 3 members out of 9 are C93 and from computer science department we have to choose 4 members, so there are 11 ways to choose 4 members out of 11 and total number of ways, in order to find the total number of ways we'll use the product rule. So by using the product rule we have this answer. Now this is the question from exercise. Question number 13. A group contains n men and n women. How many ways are there to arrange these people in a row if the men and women alternate? Now since there are n men and they can be arranged in n factorial ways, okay, taking all the men in arrangement, n factorial ways are there to arrange the men. Similarly, there are n women and they can be arranged in n factorial ways independently. Now the men and women must alternate and there are same number of men and women. So therefore, there are exactly 2 possibilities. Either the row starts with a man and ends with a woman, or a row starts with a woman and ends with a man. So we have 3 tasks to perform then. Arrange the men among themselves, arrange the women among themselves and decide which 6 starts the row. So by the product rule, n factorial multiplied by n factorial, and there are 2 ways to arrange them, one of this and one of this, so multiplied by 2. So total number of ways to arrange n men and n women, if they stand alternate each other, is 2 n factorial whole square. This is question number 19 from exercise 6.3. A coin is flipped 10 times. Where each flip comes up either heads or tails, how many possible outcomes are there in total? Okay, so in total, each flip can be either head or a tail. So there are 2, that is for every flip there are 2 possibilities and we have to do 10 flips. So total possibilities are 2 multiplied by 2 multiplied by 2, 10 times we have to multiply 2. So 2 to the power 10 times. So part B, how many possible outcomes contain exactly 2 heads? So contain exactly 2 heads and we are going to flip it 10 times. So we simply need to choose the 2 flips that came up heads. They are 10C2, which is equal to 45. Okay, so which contains exactly 2 heads, no less and no more. So in this case 2 heads are fixed and 10C2 is the total the number of ways. Uh, Next, how many possible outcomes contain at most 3 tails? Sorry, at most. I mean, at most means it can contain one tail, it can contain two tails, it can contain three tails, right? Or it can contain no tails. So at most 3 means the number of tails can be 0, 1, 2, 3. So we'll count each possibility, the number of ways in each possibility, and then we add all of them. So if there are 3 tails, the number of ways are C10 3, and if there are 2, then 2 combination of 10 objects, and then if there is one tail, then one combination of 10 objects, and if there is no tail, then C10 0, and then just calculate them, add them, and we have 176 outcomes in total. Okay, part D. How many possible outcomes contain the same number of heads and tails? Okay, same number of heads and tails means we are going to flip it 10 times, so there are 5 tails and there are 5 heads. So if we have 5 heads, then the total number of outcomes is C10 5, which is 252, and similar is the case with tails, because number of heads and number of tails is equal in these cases. Okay, question number 35 of exercise. How many bit strings contain exactly 8 zeros and 1 0, 8 zeros and 10, sorry, this is 10, oh my god. How many bit strings contain exactly 8 zeros and 10 ones? If every 0 must be immediately followed by 1. Okay, every 0 must be immediately followed by 1. So wherever 0 there is 0, there must be 1 after it. So how many bit strings contain exactly? So we have to find the number of bit strings where 8 zeros and 10 ones are there. So since there are 8 zeros, so 0 1 pairs can be 8. All right, we can form 8 pairs like 0 1. Whenever there is 0, there must be 1. So this is the possibility. One of the possibilities, it can be arranged in a way, and the rest of 2 ones can be arranged anywhere. Okay, so there is no condition on 1, but whenever there is a 0, there must it must be followed by 1. So what we have to do to implement the condition that every 0 is immediately followed by a 1. Let's think of gluing a 1 to the right of each 0. Then the object we have to work with are 8 blocks consisting 0 1 and 2 ones. Okay, so we have 10 objects in total. So this is easy to calculate for the for we simply have to choose 2 of the positions in the string to contain the ones and fill the remaining positions with 0 1 blocks. Okay, so there is its answer is C10 2, which is 45. Next section 6.4, and this consists of binomial coefficients and identities. So the subsections of this section are binomial theorem, Pascal's identity and triangle, other identities involving binomial coefficients. So first of all, binomial expressions and uh, 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 some discussion before defining or before establishing the binomial theorem. So first definition of binomial expression. And binomial expression is actually the sum of two terms like x plus y, and more generally these terms can be product of constants and variables. Now there are few remarks regarding this. We can use counting principle to find the coefficients in the expansion of x plus y to the power n, where n is a positive integer. And to illustrate this idea, we'll first look at the process of expanding x plus y cube. And you are already familiar with the expansion. So this expansion consists of the terms x cube, x square, y, x, y square, and y cube. Now, what are the coefficients of these terms? Now, so to answer this question, we can see that x cube, x multiplied by x multiplied by x. So the coefficient of x is 1. It occurs only one time, so uh, coefficient is 1. And to obtain x square y, x square y and x must be chosen from two of the sums and a y from the other. Okay, so there are three combination two ways to do this. So we have three factors here, and from 2 we are going to get x square, and y will become from third one. So 3 to do this, and so the coefficient is 3. Combination, two combination of three objects. Similarly, x y square, actually x comes from only uh, one factor from the three factors. So the number of ways are one combination out of three. So, and y comes from every uh, factor in order to make y cube. So this is 3 c3, so which is 1. So we have used a counting argument to show that x plus y cube is equal to this. And similarly, we can present an expansion for x plus y to the power n. So this is the expansion for x plus y to the power n, and which can be expanded in terms of combinations like this. And these combinations nc0 and c1 are called uh, binomial coefficients. Now, using the binomial theorem, let's solve few examples. What is the coefficient of x12, y13 in the expansion? So first of all, we will expand this using this binomial formula, binomial theorem, and then we'll find the term involving x12 and y cube. So this is the general rule. Summation varies from 0 to 25, when the combination 25j, 2x to the power 25 minus j minus 3y to the power j. Now if we compare this with this, in this case x is 2x, y is minus 3y. So we are just replacing x by 3x and y by minus 3y, and we have this result. Now, in order to make y to the power 12, we must have j is equal to 12. When j is 12, we can see that x to the power 25 minus 12 will make it 30. So in this term, when j is 12, in this term y to the power 13 occurs, as well as x to the power 12 also occurs. So consequently, coefficient of this will be 25, 13. This j also will be replaced by 13. So combination 25, 13 and 2 to the power 25 minus 13 is 12. Similarly, minus 2 3 to the power j was 13, so minus 3 to the power 13. X and y will remain as it is, because this will make x 12 and y 13, and so by evaluating this we have this coefficient. Now there is an identity that sum of all these coefficients, binomial coefficients, is 2 to the power n, and you can prove this. There are easy simple steps. Just replace x and y by 1, and we'll have this result. Next is very interesting and important identity in counting, Pascal's identity. So this states that if n and k are integers with k is less or equal to n and k is greater or equal to 0, then these two combinations, sum of these two combinations is equal to this. Now just observe the pattern here. this is nk minus 1, this is nk. These are combinations of n objects choosing k minus 1, and similarly this is the combination of n objects choosing k. Okay, now sum of these combinations is equal to, now this is n, this is n, these two must be same, so this is replaced by n plus 1 on left hand side, right? And you can see here k minus 1 k, and difference of these two is 1, right? And in this case the greater one uh, will be chosen. Okay, so if we have for example, let's have an example. If we have let me write for example, 3c2 plus 3c1, right? So this must be equal to, now 3 is common, this is replaced by n plus 1, that is 4. Okay, and what which one is greater? 2 is greater, so we write 2 here. Okay, so this is how it works, and we'll use this property to form Pascal's triangle in next slide. So that is why you need to understand the idea behind this, and proof is given here. If you are interested, you can go through this, but it is not required as such. You just need to know the application, how to apply the identity. So here is the Pascal's triangle, and just see the pattern. The nth row in the triangle, this is the triangle. The nth row in the triangle consists of binomial coefficients of nk, nck, where k is 0, 1 up till n. Okay, so initially we are going to start with n and k both are 0. So first row is 0th row. Okay, so 0, c0, and this gives us 1. So left hand side is the combination form of the binomial coefficients, and right side gives us the final form, integral form of the binomial coefficients. So first we'll start with 0, 0, and for next second row we are going to write possible coefficients with n is equal to 1, and since this is n, for n is equal to 1, this is just x plus y, so coefficient of x will be 1 c0 and coefficient of y will be 1 c1. And next is quite interesting. When n is equal to 2, there are 3 terms in the expansion. So 2c0 is the first coefficient, 2c1 is the second, and 2c2 is the third coefficient. So first and last is always 1, and we know that x plus y to the power n, first and last coefficient is always 1. Now what about the coefficients in between? Now this 2 1 becomes is actually the sum of these two. See, using Pascal's identity, 1 0 plus 1 1. Okay, see again, n k minus 1 n k, n becomes n plus 1. So see, 1 0 1 1, so 1 is replaced by 2, and we will pick greater one from the lower integrals, right? So greater one here is 1, so this is 2c1. Interesting. So 2c1 is 2, of course. When we expand x plus y whole square, x square plus 2xy plus y square, so the middle coefficient is 2. Okay, next is the expansion for n is equal to 3. For n is equal to 3, we have 3C0, 3 first and last, which is 1 and 1. Now, let's have a look at the coefficients, intermediate coefficients. So, add these two using Pascal's identity. We must have 3 and the greater one will pick greater one, which is 1. Okay, so again add these two. We have 3 and the greater one is 2. Right, so this is the pattern, and we can continue in this way, and this triangle is called Pascal's triangle. This is actually the triangle of coefficients, and it has relation between like every expansion has a relation with the previous one and the next one as well. So by Pascal's identity, adding two adjacent binomial coefficients results is the binomial coefficient in the next row between these two coefficients. See? So next result. Uh, Actually, now we are learning few identities involving binomial coefficients. First identity is Vermont identity, and in this case we must have m and r, and all are non-negative integers with r not exceeding either m or n, that is r is less than or equal to m, or r can be less than or equal to n, but not greater than mn. So sum of all such products mr minus k and nck, sum of all the products where k varies from 0 to r is equal to m plus n r. Okay, uh, here we can add both, and we will have r, and adding these two m and n, we have m plus n. So adding all the products, we have this result. So keep it in mind, and we'll use it in further applications. Using this corollary of this theorem, this identity is 2ncn, which is equal to summation of nck square, where k varies from 0 to n, and this is actually directly coming from this identity by taking m is equal to r is equal to n to Vermont's identity, and we have this result. So this is quite straightforward. Uh, Other identities again involving binomial coefficients. Next identity is if we add all these coefficients jr, where j varies from r to n, we have this result: n plus 1, r plus 1. Now there are a few questions regarding this section. These are questions actually from exercise of the section 6.4. So question number 7 of the section 6.4, and question is, what is the coefficient of x9 in this expansion? And the same methodology will be followed. We actually learned in some example in previous slides. So first of all, we have to check where for which power of x, actually x to the power 9 is required, right? And let me write something in case in this case we have actually our binomial theorem looks like this: x plus y to the power n. Now in this case n is equal to 19. If you want to compare it with the binomial theorem, x is equal to 2 and y is equal to minus x. Now just compare it, and for x is equal to 9, we'll have this term. Now the coefficient is, since negative x to the power 9 is negative, so coefficient must be negative. 2 to the power 10 as it is, and this combination, after solving this combination, we'll have this result, which is the answer. And next, question number 25, and this is also from exercise 6.4. So let n be the positive integer, show that prove that this identity. Okay, now in order to show that, we consider left hand side. and left hand side can be written in this form. And what we did, we used this result. Okay, by using this result, this sum can be written in this form. Now next what we did, we just multiplied by 2 and divided by 2 in order to have this 2. So actually what we did was to and divided by 2. So 1 by 2 comes outside, and this 2 times this combination can be written as 1 plus 1. Okay, 2 can be written as 1 plus 1. So this is how this is arranged. Okay, next what we did, first term as it is, and the next term by using this result. We wrote this. Okay, 2n plus 1 combination n, 2n plus 1 cn, right? 2n plus 1 cn can be replaced, cn plus 1 can be replaced by 2n plus 1 cn, right? So when we add these two, n minus r and r, we should have n, because this is the complement of r. So in this case, you can see if we add these two, n plus 1 and n, we have 2n plus 1. So this works. Okay, now last step. In last step again, we use this identity to have this. Now 2n plus 1, 2n plus 1. So we'll add 1 in this. So we have 2n plus 2 here, and we'll pick greater one. So since n is positive, so n plus 1 is greater than n. So we have n plus 1. Okay, and this is the right hand side. Okay, next 6.5 article, and this is about generalized permutations and combinations. So in this section we are going to learn permutations with repetition, similarly combinations with repetition, permutations with indistinguishable objects, and distributing objects into boxes. So there are 4 subsections of this section. So first of all, permutations with repetition, that is, if repetition is allowed, then how to use the permutation. Repetition is allowed and order matters, right? Permutation means order of the order of the objects matters in the arrangement. If we change the order, it is a different arrangement altogether. So order matters and repetition is also allowed. So first result, the number of R permutation of a set of n objects with repetition allowed is n to the power r. Okay, so in order to fill r spaces, we have n objects, and since repetition is allowed, when we fill first space, we have n choices. In for the second space, we still have n choices because repetition is allowed. Again, for third space, we have n choices, and so on up till r spaces, we have n choices for every space to fill. So in total, we have n to the power ways to arrange the objects with permutation with repetition allowed. So, for example, how many strings of length r can be formed from the uppercase letters of English alphabet? Okay, how many strings of length r can be formed from the uppercase letters of the English alphabet? And number of English alphabets is 26, and since repetition is allowed, there is no restriction on it. So, if we are required to form strings of length r using alphabets. So since length is r, so first space can be filled in 26 ways, and so on. There are 26 choices for every space out of r spaces. So r permutation, so number of r permutation of set is uh, 26 to the power r. So there are 26 to the power r ways to form the strings. That is the number of strings, the total number of strings is 26 to the power r. Okay, next, this is a very interesting and a bit tricky idea. combination with repetition. Actually, you are already familiar with permutation with repetition. You would have learned in your intermediate level or A levels might be. But this is, I don't know, I think this is the new idea for you. So let's see how it works. How many ways are there to select 4 pieces of fruit? How many ways are there to select 4 pieces of fruit from a bowl containing apples, oranges, and pears? If the order, how many ways are there to select 4 pieces of fruit from bowl containing apples, oranges, pears? If the order in which the pieces are selected does not matter, only the type of the fruit and not the individual pieces matter. Okay, type of the fruit actually matters. It will be counted, and there are at least 4 pieces of each type of the fruit in the bowl. So we have three. We have a bowl in which 3 types of fruits are there, and there are 4 pieces of each type of fruit, right? And we have to choose 4 pieces of fruit, right? So let's try to write down all the ways. First case maybe to have 4 pieces of one fruit, like 4 apples, 4 oranges, or 4 pears. Okay. Second case can be 3 pieces of one fruit and one of another fruit. So 3 apples, 1 orange, 3 apples, 1 pear, 3 orange, 1 apple, 3 orange, 1 pear, 3 pear, 1 apple, 3 pear, 1 orange, right? And the next case can be 2 pieces from one fruit and 2 pieces from other fruit. So these are the cases: 2 apples, 2 oranges, 2 apples, 2 pears, 2 oranges, 2 pears. And the last case is 2 pieces from one fruit and 1 piece of another and 1 piece of third fruit, right? So there are 3 types of fruits. So this is also possible. So it may contain 2 apples, 1 orange, 1 pear, and 2 oranges, 1 pear, 1 apple, 2 pears, 1 apple, one. So we have 15 ways. Okay. So what happened here? We had to choose 4 pieces. That is, this is going to be the problem of 4 combination. But what is n in this case? N must be, we have 3 types of fruits. Okay, we have 3 types of fruits, and we have 4 pieces of every type of fruit. Okay, so in total, uh, we can arrange them. 3 types of fruits can be arranged by putting 2 dividers among them. So we have 2 cases here and 4 types. So total we have 6 plus 2. So n is 6. Or you can say n can be found by 4 plus 3 minus 1. Okay. So let's see. Let's try to understand from another example. How many ways are there to select 5 bills from a cash box containing $1 bills, $2 bills, $5 bills, $10 bills, $20 bills, $50 bills, and $100 bills? Assume that the order in which the bills are chosen does not matter, that the bills of each denomination are indistinguishable, and that there are at least 5 bills of each type. So types of bills are 5. Okay. How many ways are there to select 5 bills? And we have to select 5 bills. Types of bills are 1, 2, 3, 4, 5, 6, 7. Types of bills are 7, and we have 5 bills of each type. Okay. So how to do this? Now the order in which the bills are selected does not matter. All right, this is given, and we have 7 different type of bills as we just counted. and these can be selected as many as 5 times, right? We have to select 5 bells out of this. So this problem involves actually counting 5 combination with repetition allowed from a set with 7 elements, right? So listing all the possibilities, of course, is not possible. This is going to be a hectic job. So uh, what we did, we made these blocks, and each block consists of one type of bills. This consists of $100 bills, this consists of $50 bills, this consists of $20 bills, and this consists of $10 bills, and this consists of $2, and this consists of $1 bills. So uh, these are called, you may call it compartments. Okay, in your book the word compartment is written. So these compartments can be separated by 6 devices: 1, 2, 3, 4, 5, and 6. Okay, so these compartments can be divided by 6 separators. There are 6 dividers. So we have 6 divisors, we have to choose 5. So r is 5, so n is 6 plus 5, which is 11, right? So we can choose these, we can write 5 permutation formula as shown here, C11 5. This is by using formula we can calculate this, and we have 462 total number of ways to choose the choose 5 bells with 7 type of bells. Okay, so this leads us to the theorem, which is this general form. The number of R combinations from a set with n elements when repetition of elements is allowed. Okay, the number of R combinations from a set of n elements when repetition is allowed is n plus r minus 1 CR. So add n and r and subtract 1. Okay, so n plus r minus 1 CR, and this is also equal to n plus r minus 1 C n minus 1. This is just like the rule, complement rule. Okay, so this is the formula you need to remember. Okay, so let's have another question. This is an example in your book. How many solutions does the equation x1 plus x2 plus x3 is 11? Okay, now this is the problem. Let me write complete question. Where x1, x2, x3 are non-negative integers. So keep it in mind. This is very important. x1, x2, x3 are non-negative integers. They can be 0, they can be positive integer, but they cannot be negative integer. So each solution corresponds to a way to select 11 items. So we have to make it 11 items, adding all x1 is one type, x2 is second type, x3 is third type. So we have to choose 11 items from these 3 types. So this is the problem. So see, our R here is 11. So this is the problem of 11 permutation, and n here is 3. So when we add 3 plus 11 minus 1, so repeated combination formula allows us to write this. 3 plus 11 minus 11, see 11, and rest is actually a matter of calculation, and we have 78 answer. Next, combination with repetition. Again there is a question. Suppose that a cookie shop has 4 different kind of cookies. How many different ways can 6 cookies be chosen? Now type of cookies are 4. Okay, so we have to choose 6 cookies. So R here is 6, right? And 6 combinations are found when repetition is allowed, and we have how many types? 4 types of cookies. So n is 4. So 4 plus 6 minus 1, which is 9, and rest you can calculate easily by using formula. So there is a table of formulas for counting permutation combinations with and without repetition. So our permutation, when repetition is not allowed, we have this formula. When our combination with repetition is not allowed, we have this formula. Our permutation, when repetition is allowed, we have this formula. Our combination, when repetition is allowed, we have this formula. So these are the four major formulas you have to uh, remember, that you have to memorize actually in order to apply in the questions of counting. Okay, next, permutation with indistinguishable objects. How many different strings can be made by recording the letter of the word, reordering, sorry. How many different strings can be made by reordering the letters of the word SUCCESS, that is success? Okay, now they are repetitions. S lies 3 times. Okay, C is repeated. C occurs 2 times in this word success. So there are 7 possible positions for the 3 S's and 2 C's, 1 U and 1 E. Okay, so the 3 S's can be placed in C73 combination 7C3 different ways, leaving 4 positions free. Okay, the 2 C's can be arranged in C4 ways, and U can be arranged in C2 one ways. Sorry. And E can be arranged in C1 ways, and the total number of ways, we will just multiply all the ways to get the total number of ways, which is 420. Now, permutation with indistinguishable objects. So there is a theorem. This is also very important. The number of different permutations of n objects where there are n1 indistinguishable objects of type 1 and 2 indistinguishable objects of type 2 and up to n k indistinguishable objects of type k is n factorial divided by n1 factorial, n2 factorial, nk factorial. So this is the formula. If the number of different, if we have to find the number of different permutations of n objects where they are n1 indistinguishable objects of type 1 and 2, that is n1 objects are repeated, n2 objects are repeated, and so on. So if we have multiple objects which are repeated, then we have this formula for permutations. Distributing objects into boxes. So many counting problems can be solved by counting the ways objects can be placed into the boxes. So the object may be either different from the other, distinguishable, or identical. Indistinguishable. Okay. Indistinguishable mean identical, and distinguishable means they are different from each other. We can distinguish them. The box may be labeled distinguishable or unlabeled indistinguishable. Okay. So distinguishable objects and distinguishable boxes. So first case, distinguishable objects and distinguishable boxes. So there are n factorial over n1 factorial, n2 factorial, and k factorial ways to distribute n distinguishable objects into k distinguishable boxes. Okay, so there are 52 factorial over 5 factorial, 5 factorial, 5 factorial, 3 the 32 factorial ways to distribute hands of 5 cards, each to 4 players, right? So if we have 4 players, then 5 factorial, 5 factorial, 5 factorial are distributed to 4 players, and the rest of the cards are 32. 30 and the rest, the fifth player will get, which is not in count, they will get 32 factorial. So there are 32 factorials actually to arrange the rest of the cards. So this is the example of distinguishable objects and distinguishable boxes. Now, indistinguishable objects and indistinguishable boxes, now there are Cn plus r minus 1, n minus 1 ways to replace our indistinguishable objects into n distinguishable boxes. So there is an example. There are 8 plus 10 minus 1 C10 that is 10 plus 8 is 18, 17. So 17 C10 ways to place 10 indistinguishable objects into 8 distinguishable boxes. So these are the formula for distinguishable and indistinguishable uh, uh, objects, boxes and objects respectively. And this is the formula for distinguishable object in distinguishable boxes. So distinguishable, next combination, distinguishable objects and indistinguishable boxes. Okay. There is another case, indistinguishable objects and indistinguishable boxes. So we don't have a specific rule for this. So such problems can be handled individually. So if we come across such a problem, then we can discuss it. So there are a few questions from exercise. How many solutions are there? This is question number 15 of exercise. How many solutions are there to the equation x1 plus x2 plus x3 plus x4 plus x5 is equal to 21, and where xi is non-negative integer such that first condition is non-negative. They all are non-negative, but there are more conditions applied on few of the variables. So first part, all are non-negative, but x1 is greater or equal to 1. This is non-negative, but there is another condition imposed on x1, which is x1 is greater or equal to 1. Now, in order to solve the problem, we have to make all the objects greater or equal to 0. Okay. So x, in this case, x2 is greater or equal to 0, x3 is greater or equal to 0, x4 is greater or equal to 0, x5 is greater or equal to 0, but x1 is greater or equal to 1. So we have to substitute something, or we have to replace x1 by some number for which is greater or equal to 0, if it makes sense. X1 greater or equal to 1. That is, if we replace x1 by x1 prime plus 1, okay, then x1 prime plus 1 or x1 dash plus 1 is greater or equal to 1, and this makes x1 dash greater or equal to 0. So we can replace x1 by x1 dash plus 1 in the equation, and the new equation will be this x1 dash x2 x3 x4 plus x5 is equal to 20. Now we have the problem of choosing 20 objects out of these 5 types. So the number of ways are 5 plus 20 repeated combinations case, 5 plus 20 minus 1, and r here is 20. So by solving we have this number of ways. And next part, same equation, and all xi's are non-negative with the condition xi is greater or equal to 2 for I is equal to 1, 2, 3, 4, 5. That is, for every x, xi is greater or equal to 2. So we have to transform every x into a new integer which is greater or equal to 0. So xi is equal to xi dash plus 2, and then we'll replace the equation by all the new xi's, and we have this new equation. And again we have to choose, we have to collect 11 objects out, of these 5 types. So again repeated combination problem. So 5 plus 11 minus 1, C11, and by using the formula and calculating it, we have 1365 the answer. Next part C, x1 is greater or equal to 0 but less or equal to 10. This is interesting. X1 is less or equal to 0 and less or equal to 10 and greater or equal to 0. Okay. So we have to collect 21 objects out of these 5 types, and if there is no restriction, that is there is no upper bound, greater or equal to 10, then we have total number of ways 5 plus 21 minus 1 C21, which is 12650. Now we have to subtract the ways uh, which for which xi is greater or equal to 11. Okay, this is easy to actually find out. X1 is greater or equal to 11. This condition is imposed only on x1. So this is the total number of ways without any restriction, and now we will find the ways with x1 greater or equal to 11, and then we will subtract both of them to find the number of ways for which x1 lies between 0 and 10. I hope it is understandable. So do have a look at it, and if there is a problem you can let me know. And next, similarly, x lies between 0 and 3, x2 lies between 1 and 4, x3 is greater or equal to 5. So you can solve it one by one, and I'll share the solution. So I hope you can understand it now, because we have already discussed it in detail. Okay, let's move further. There is question number 23 in the exercise. How many ways are there to distribute 12 distinguishable objects into 6 distinguishable boxes so that the two objects are placed in the boxes? So first we choose the two objects to go to the box number 1, and for this we have 12 C2 ways, and then choose the two objects to put into the box number 2, and for this we have 10 C2 objects, because 2 has already been dropped into the box number 1, and then choose the uh, two objects to go to the box number 3. Now we are left with 8 objects, so 8 C2 ways, and so on. After multiplying all these possibilities, we have this answer, and this is the final answer. And that's all for today. Good luck. If you have any problem, you can let me know. Thank you. Bye bye. Allah Hafiz.